So what I want to talk to you today about is how the resting membrane potential is established inside of a cell. This is relevant for discussing neurons. It's relevant for discussing the sinoatrial node. It's relevant for discussing really any cell that has a charge. But understanding how you get there is relevant to any discussion in physiology. If you don't understand how you get there, then understanding anything else, frankly, doesn't make a whole lot of sense. So we can get through this relatively quickly, actually, and let's go ahead and get started. The first thing that you have to understand, there's really two things, two forces that you have to understand with establishing the resting membrane potential, and that is the chemical and electrical driving force. So the chemical driving force, spelled just like it sounds, chemical, is nothing more than a diffusion gradient. So for example, if sodium ions are high outside of the cell and sodium ions are low inside of the cell, what's going to happen is sodium is going to want to go from the outside in. Simple as that. That is the chemical driving force in this situation. Now, if the opposite were true, without erasing this, right, and sodium were high inside and low outside, then what would happen, right, is sodium would want to go from the inside out. All right, so the chemical driving force, again, is really nothing more than a diffusion gradient. It's really as simple as that. The other force that we need to discuss is what's known as the electrical driving force. So again, we've got this hypothetical cell here, and inside of this hypothetical cell, we're going to say that there's more positively charged molecules and ions on the inside than there is negatively charged molecules and ions. Okay, so if there's more positively charged molecules and ions on the inside than there is negative, this particular cell is going to have a net positive charge. Their inside is going to be somewhat of a positive charge. Okay, well, that would mean that on the outside of the cell, in the extracellular fluid, then there's going to be somewhat of a negative charge. Okay, so what about this electrical driving force then? Well, let me get rid of this real quick. Let's pretend that there are sodium ions, right, and the inside of the cell. We know that the inside of the cell has a net positive charge, and we know on the outside of the cell there's going to be, of course, then a slightly negative charge. So what this tells us then, and by the way, there's going to be a negative charge in relationship to the inside. That's all I'm saying. What this tells us then is that sodium ions on the inside are going to get pulled through their electrical driving force from the inside out, right? Opposites attract. So if the outside has a slightly negative charge, sodium is going to want to go from the inside out. And on the opposite end, well, how about chloride ions? Okay, they have a negative charge. Well, the electrical driving force is going to pull chloride in. Right? The inside has a net positive charge. Chloride is a negatively charged ion. It's in the exterior, right, in the extracellular fluid. So that electrical driving force is going to pull chloride from the extracellular fluid into the intracellular fluid. Okay, so these are the chemical and electrical driving forces. Chemical driving force, really simple, just the diffusion gradient. Electrical driving force, it just depends, right? Is the inside positive or negative, and is the ion positive or negative, and that will tell you which direction it's going to get pulled. All right, so those are the first two steps. And now we can really start playing with two important ions for establishing membrane potentials, which are sodium and potassium. So here's what we know about cells when we talk about the development of a cell's resting membrane potential. We have this theoretical cell here, and on the inside of the cell, there is the same number of positively charged molecules and ions as there is negatively charged molecules and ions. Exact same number. Okay? So if I were with you, I'd say, what do you think the charge is inside of the cell? It's nothing. It's neutral. Okay? There's the same number of positive and negatively charged ions on the inside of the cell, so there's no charge at all. There is no, in this circumstance, electrical driving force. And I would say the same thing is true for the outside. There's the same number of positive and negatively charged ions on the outside. So there's no charge in the extracellular fluid or the intracellular fluid. Again, this is just hypothetical for coming up with this ultimately to get to where we're going, excuse me. Okay, so both neutral, intracellular and extracellular fluid, no charge, so there is absolutely no electrical driving force in either direction, no matter what the particular ion is. Okie dokie. Now we're going to focus on sodium and potassium. Let's do potassium first. When we talk about potassium, K plus, what we know about potassium is that potassium is really high inside of the cell, and it's really low outside of the cell. Okay, there is no electrical driving force. The same number of positively charged ions and negatively charged ions is located in the intracellular fluid. Same is true for the extracellular fluid. So there is no electrical driving force. But what is there? Right? There's a big chemical driving force because potassium's high inside and low outside. So what does that tell you? Potassium's going to want to go from the inside out through its chemical driving force. And we're going to pretend that this cell is really permeable to potassium. That means that there's going to be lots of potassium channels, potassium pores, leak channels. We call this diffusion through pores. All right, so we're pretending that this cell is only permeable to potassium. And what do we know? Well, potassium's high on the inside, low on the outside. So through its chemical driving force, it's going to start going from the inside out. Okay, great. If potassium starts going from the inside out, it's leaving the cell. What I would ask you in person is, what do you think happens to the proportion of positively charged ions and negatively charged ions on the inside? Well, positively charged potassium ions are leaving through their chemical driving force. As more and more potassium leaves, what's going to happen? The proportion is going to get thrown off of positively charged and negatively charged ions. There's going to be more negatively charged ions than there are positively charged ions as more and more potassium exits. So what do you think happens to the inside of the cell is what I would say. I hate doing this without people. But what happens is the inside starts to become negative. Right? There starts to become a net negative charge on the inside. Because potassium is leaving, and now on the inside there's more negatively charged ions than positively charged ions. Now the inside is going to start to become negative. All right, so let's talk about what's going to happen. I need to erase some stuff. Okay, so as more and more potassium leaves, the inside becomes more and more negative. All right, so If the inside's becoming more and more negative, what's developing on the inside is a electrical driving force. Right? Because if the inside is becoming more and more negative, now what's happening is an electrical driving force is developing. So, what's potassium? Potassium is a positively charged ion. So as the inside becomes more and more negative, now there is an electrical driving force to bring potassium back into the cell. Okay, there's potassium out here. There's now an electrical driving force developing to bring potassium back. And what it really does is it slows down the rate that potassium leaves. Right? Because potassium is leaving through its chemical driving force. As it keeps leaving, the inside becomes more and more negative, and electrical driving force develops, and that slows down the rate that potassium leaves because it's pulling it backwards through an electrical driving force. And here's what happens. Eventually, the cell hits negative 94 millivolts. And when the inside hits negative 94 millivolts, you have established something that's known as an equilibrium potential. When the inside is at negative 94 millivolts, the drive for potassium to leave through its chemical driving force equals the drive for potassium to come back through its electrical driving force. So an equilibrium potential is when the chemical driving force and the electrical driving force for an ion are equal. So at negative 94 millivolts, potassium doesn't exit or leave the cell. Right? It's at negative 94, what happens is we're just in limbo. Potassium is no longer leaving, potassium is no longer coming in. Because the drive for it to go out is just as strong for the drive for it to come back in. Its chemical driving force to leave equals its electrical driving force to come back, so it's stuck. The cell gets stuck at 94 millivolts. Potassium's equilibrium potential. And now we can move on to sodium. Here's what we know about sodium. Sodium is really high outside of the cell, and it's really low inside of the cell. It's the opposite of potassium. Okay, we're back to the beginning here, right? This is like we're back to this hypothetical situation where the number of positively charged and negatively charged ions on the inside is equal, so there is no positive or negative charge inside of the cell. The same is true for the extracellular fluid. The number of positively charged and negatively charged ions and molecules on the outside is the same, so there is no charge, right? There's no electrical driving force. Obviously, the distribution of particular ions in the extracellular and the intracellular fluid is not equal. But the total number of positively charged and negatively charged ions on the inside and the outside is equal. Okay? So, for example, just like we did with potassium, there is a high concentration of sodium in the outside and a low concentration of sodium in the inside. To start with, there is no electrical driving force. Right? The fluid in the extracellular fluid is neutral. The fluid in the intracellular fluid is the fluid that makes up the intracellular fluid is neutral as well. Now we're going to pretend that this cell again is really permeable, specifically to sodium. There's a lot of sodium channels, sodium pores. Okay, so there's no electrical driving force to start, but there's a big chemical driving force. So what's going to happen here is sodium is going to go from the extracellular fluid into the intracellular fluid. And what do you think is going to happen? That's probably what I would say. As more sodium comes from the extracellular fluid into the intracellular fluid, what's going to happen to the proportion of positively charged and negatively charged ions on the inside? You're going to increase the number of positively charged ions in relationship to the number of negatively charged ions, right? Because sodium is coming from the extracellular fluid into the intracellular fluid through its chemical driving force. As sodium comes in through its chemical driving force, you're bringing sodium ions into the cell and increasing the number of positively charged ions in relationship to negatively charged ions. So what do you think is going to happen to the interior? It's going to start developing a net positive charge. The inside of the cell is going to start to become positive. Okay, so let me erase this real quick and get to where I'm going with this. So sodium is coming in, and it's making the interior more positive because we have positively charged ions entering, increasing the number of positively charged molecules and ions in the inside in relationship to negative. Okay, so the inside is becoming more and more positive. What does that mean for the extracellular fluid, right? It's becoming more negative. Okay, we can't really measure the extracellular fluid with a probe. We can only measure the inside of the cells, really. This is the way that we understand them. So we have to look at the charge on the inside. Okay, so as sodium comes in, what we know is once enough sodium comes in to make the interior positive 60 millivolts, what's happened is the outside has become negative enough, right? Because as sodium's coming in, now we're increasing the number of positively charged ions on the inside in relationship to negative, so the inside's becoming positive. But what's happening to the extracellular fluid, right? As positively charged ions are going from the extracellular fluid into the intracellular fluid, the number of negatively charged ions on the outside is now increasing in relationship to positive because positively charged sodium ions are coming in. Okay, so the outside is becoming negative while the inside is becoming positive. And once we hit positive 60 millivolts on the inside of the cell, we have reached what's called, again, the equilibrium potential for sodium. The drive for sodium to come in through its chemical driving force equals the drive for sodium to go back out through its electrical driving force. Right? The outside has become so negative now that it's pulling these positively charged sodium ions backwards. Right? It's pulling these positively charged sodium ions back towards the extracellular fluid. So at positive 60 millivolts, there's no longer any movement of sodium because the drive for sodium to come in through its chemical driving force equals the drive for sodium to go out through its electrical driving force. Okay, so there you have it with equilibrium potentials for sodium and potassium. And now, after you understand what a chemical and electrical driving force is, and after you understand what a chemical and an electrical driving force is, you can understand how the equilibrium potentials are established for sodium and potassium. And then finally, you can look at a cell and figure out how do we get to this resting membrane potential. So let's do that. So here we go. All right. You've got a cell like so. On the inside of the cell, there's the same number of positively charged ions as there is negatively charged ions. So the inside has no charge, right? It's neutral. Same is true for the extracellular fluid. Same number as positively charged ions and negatively charged ions. So the extracellular fluid is also neutral. But just because there's the same number of positively charged ions and negatively charged ions on the inside, or in the intracellular fluid, as is true for the extracellular fluid, does not mean the distribution of all ions is equal, which is what I've been trying to get at, and hopefully I've been explaining good enough, right? For example, in the inside of the cell, there's a really high concentration of potassium ions on the inside, and there's a really low concentration of potassium ions on the outside. And the opposite is true for sodium. There's a really high concentration of sodium ions on the outside and a really low concentration of sodium ions on the inside. Okay? So there's no electrical driving force to start, right? The inside has a net neutral, I just can't call it net, it has a neutral charge. There's no positive or negative charge. So is true for the outside. But there are big chemical driving forces. There's no electrical driving force to start at all. Right? Intracellular fluid is neutral, extracellular fluid is neutral. But there's a huge distribution of particular ions that are higher on the outside, lower on the inside, higher on the inside, lower on the outside. So there are big chemical driving forces. There's just no electrical driving forces to start. Okay, so when we look at a cell, this is what we see to start. High potassium on the inside, low potassium on the outside. Low sodium on the inside, high sodium on the outside. Just like the two examples that we went through. This is true for all cells. So what do we know? There's no electrical driving force at all to start, but there are big chemical driving forces. There's a big chemical driving force for sodium to come in, and there's a big chemical driving force for potassium to go out. Right? So potassium wants to go out, sodium wants to come in. But here's the thing, and I'm going to pause this for a second so that I can erase a little bit. Our cells are way more permeable to potassium. There are way more potassium channels, potassium leak channels, whatever you want to call them, located within the plasma membrane. So let me show you what I mean. Okay, each one of these is a channel. Our cells are about 25 times more permeable to potassium. Okay, so if we were looking at this, this would be a potassium channel, this would be a potassium channel. So with this, maybe here's one sodium channel, potassium, 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 maybe one sodium here, potassium, 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 sodium. Okay, so when I look at all of these, since maybe you can't see them so well, there's only this channel here, and this is not even close to being drawn to scale. It's, if we're talking about 25 to 1. The only 3 channels for sodium I've highlighted here. The rest are all for potassium. So our cells are far more permeable to potassium than they are to sodium. Okay, so what does that mean? Let me erase this again real quick. If our cells are much more permeable to potassium than they are for sodium, think about the chemical driving forces. Potassium wants to leave from the intracellular fluid to the extracellular fluid. Sodium wants to come in from the extracellular fluid into the intracellular fluid. Okay? They both have big chemical driving forces. But if the cell is way more permeable to potassium, what do you think that means? There's way more channels for potassium to leave through than there is for sodium to come in through. Okay, imagine you have 2 balloons. If you poke 3 holes in one balloon, and you poke 20 holes in another balloon, which one is going to lose the water faster? Obviously the one with 20 holes versus the one with 3. Okay, so if potassium is way more, if the cell is way more permeable to potassium than to sodium, that means that potassium is going to leave at a much greater rate than sodium is going to come in. Okay? That's what that means. They both have big chemical driving forces. Sodium really wants to come in, potassium really wants to go out. But the cell is 25 times more permeable to potassium. So potassium leaves at a much faster rate than sodium comes in. Okay. What do you think that means for the inside of the cell? If more potassium is leaving than sodium is coming in, potassium is leaving at a faster rate than sodium is coming in. That means more positively charged ions are leaving than positively charged ions are coming in. So what does that mean? It means that the inside of the cell is going to start to become negative. Right? Because we started off with an even distribution of positively and negatively charged ions. And now what we have is we have potassium leaving at a much faster rate. So we have a positive ion leaving at a much faster rate than a positive ion is coming in. So we're losing positively charged ions on the inside, the proportion of them. So the amount of negatively charged ions on the inside is going to go up, and the amount of positively charged ions on the inside, right, it's not going to go down, but I guess it is going to go down. Jeez. I said that incorrectly. I'm sorry. Let me restate that. Since I'm not making this on a PowerPoint video, I can't just redo a section of it. Okay? So, more positively charged ions are leaving than positively charged ions are coming in. Right? So, a number of negatively charged ions on the inside isn't changing. What's changing is the number of positively charged ions, right? If more positively charged ions, potassium, right, are leaving than positively charged ions, sodium, are coming in, we're losing positively charged ions on the inside. Right? So proportionately, since we're losing positively charged ions, since so much potassium is leaving and the sodium coming in isn't making up for it, the inside is going to start to have a disproportionate number of negatively charged ions in comparison to positively charged ions, since we're losing more positively charged ions and we're not making up for them with the number of sodium ions that are coming in. Okay, so the proportion of negatively charged ions is now going to be higher than the proportion of positively charged ions. So what we end up with is the inside is now going to develop a net negative charge. All right, 1 second. As more and more potassium leaves at a faster rate than sodium comes in to make up for the number of positively charged ions leaving, the inside is going to become more and more negative because we're losing positively charged ions. Okay, so what's happening at the inside of the cell? We're developing an electrical driving force. Okay, the inside of the cell is becoming more and more negative. What's that going to do? As the inside becomes more and more negative, it's going to start to pull potassium backwards, because potassium is a positively charged ion. Okay, so potassium is going to start leaving at a slower rate because the inside is becoming negative and pulling those potassium ions backwards. And what about sodium? As the inside becomes more and more negative, sodium is a positively charged ion, so as the inside becomes more and more negative and an electrical driving force is developed, that's going to start pulling sodium in at a faster rate. So as the inside becomes more negative, we slow down the rate that potassium is leaving, right? Because we're pulling it backwards. It's trying to leave through its chemical driving